When Uber was a small company, there was just a small group of mobile engineers, and they could really easily communicate with each other and share knowledge. It wasn't much of an issue. And that team could build one app in one repo using the tools that made sense at the time, like Ant and Eclipse. And that app was a really small app with a really tight focus. It was just a great, solid MVP. And as that team grew quickly with the business, going from one Android team to multiple teams, including a platform team with multiple standardized around an MVC architecture, and they used modern tooling for the time. These components were very well composed, and they allowed for new engineers to develop against the solid principles. And over time, one app became multiple apps across different repos. And common code was extracted to create a library that both of the apps could use as a dependency. And that common code was modularized into multiple core library repos that were consumed as versioned dependencies. And with new contributors and a good foundation, they could scale and quickly launch product offerings. And all of that organic growth became massive, with literally hundreds of mobile engineers contributing to a small number of applications. New pain points emerged regularly. Tribal knowledge fell short, communication broke down, and the organization slowed to a crawl. Many more controllers were added to the architecture. And this caused bottlenecks to emerge, where some became bloated with scoped objects in the graph. They would be coupled to more downstream dependencies, creating a large number of unmaintainable classes. And the iteration process slowed to a crawl, requiring updates of downstream dependencies, multiple sequential CI jobs, and then updates to multiple top-level apps. Developer productivity took a large hit, and architectural silos emerged throughout the company. And the product choices continued to follow this organic growth model, essentially creating a kitchen sink of products for the end user, with little focus on usability. The number of products in the bottom sheet became a joke for many in the industry. And at this point in 2016, we knew that this sort of growth couldn't be allowed to happen unchecked, and that scale had to be planned for. And at this crossroads in 2016, we decided to rewrite and redesign the Writer app at the same time. This would create a product that could be built on for years to come. And this talk today is going to cover how we took a step back to approach this opinionated scaling and the tools and processes that we've used and open sourced that will help you prepare to scale an app without over-engineering it. So today I want to talk about a few major areas of scale that we've made headway against. First, we'll discuss our project structure and build needs. And then we'll talk about RIBS, our architecture solution and the backbone of our modern apps. And I'll finally discuss some of the libraries and tools that we've used to facilitate faster mobile development. This will in no way be an exhaustive list, or I'd have to be here all day. Instead, I'm going to cover them at a high level, and then at the end, I'll link to further resources so that you can dive in on your own. Be thoughtful about what your own scaling needs are here and what you need to prep for. Don't over-engineer. You may have noticed in my first slides that we more or less started in a monorepo, or at least a single repo, and then we split out into a multi-repo structure. Like many other companies at this scale of mobile development, we eventually considered the trade-offs of a monorepo versus multiple repos. Many of the developer productivity issues that we were facing could be identified as working across multiple repos. And the three major pain points that we were feeling were issues with transitive dependency, the emergence of multiple types of architectures and conflicts among different projects as teams worked in more isolation, and long build times as the build system was inefficient at parsing and building a sub-modularized codebase. To demonstrate a problem in a multi-repo world, let's assume we have an app with a chain of transitive dependencies. If an API breaking chain is made in a downstream dependency, we'll need to make it in each library up the chain, with a commit, waiting for a CI build, and deploying to Maven or Artifactory before moving on to the next one in the chain. Clearly, this is inefficient, and it assumes the best case scenario where it is properly updated. More common is the scenario where we have two build scripts for an app and a library that the app uses. As you'll start to notice, we declare a number of fundamental libraries like storage and networking with certain versions. And immediately you see transitive conflicts through libraries that they are pulling in. Gradle will try to by default, Gradle will try to resolve conflicts in versioning by using the latest. So we can't guarantee what that behavior is going to be at runtime if the downstream didn't meet what was expected. So these pain points drove our decision to move from a series of multiple repos to one large monorepo per platform. This new project layout gives us the ability to update across multiple modules in one fell swoop and increase developer productivity. For example, here would be a similar example to the mini repo example I gave a moment ago. But here we guarantee that all of our downstream libraries are pointing to the same version of a module. In addition to the project structure, to maximize gains for our developers, our developer experience team invested heavily in converting our build system to be primarily driven by Gradle to Buck. While Gradle has made tremendous gains in tons of performance with modularized code bases, at our scale of over 1,000 modules, Buck still gives us better performance and fine-tuning. If you're not familiar with Buck, Buck was built by Facebook, and it allows a similar architecture to Bazel, Google's monorepo build system. Its build architecture is based on cacheable outputs. And Buck encourages many small modules that are highly parallelizable. It'll use all the cores on your CPU. I know, I've been listening to streaming music and had it completely stutter. Because it's so parallelizable, it can cache the outputs of the small modules. It's very fast, and it can use advanced features like network caching as well to make it even faster. Buck also has pretty good IntelliJ integration to keep a productive workflow, including concepts like building, deploying, running tests, and using unloaded modules for a large project by generating the IML files automatically. Buck is more focused than Gradle, though, making it possible to attain greater speeds under certain scenarios, but making it less flexible overall. It's also notoriously more obnoxious to configure the build scripts. Because of this, I say Buck is like rocket skates. You'll go really fast, but you don't want to change direction or fall down. To address the hard-to-configure scripts and lack of features like dependency management in Buck, let me tell you about our open source project called OKBuck. OKBuck is a Gradle plugin that you can add to your Gradle scripts following the standard pattern. And then you can execute a Gradle task that will generate a Buck wrapper object. This will configure your project and create Buck config scripts per module, eliminating the need to write nasty configs yourself. Running the Buck wrapper also has multiple advantages. It downloads, installs, and updates Buck to the latest version for you automatically. It has minimal overhead to decide when to run by using a daemon that's watching the files. It handles the task gracefully when OKBuck needs to stop or restart the daemon. And the speed of Buck is in a hypermodularized code base is given to you using this while you still maintain the simplicity and the flexibility that Gradle provides you for things like dependency management. Another great feature when using Buck build system is a tool called exopackage. Now, it's used for development builds. Exopackage constructs a shell application where each module's dex file can be hot swapped out. This allows for much smaller changes to be deployed to the device, similar to Instant Run, but it works consistently. Here on the first run, the APK builder will construct the entire shell and deliver a full install. And then on subsequent compiles, it will only send the changed dex files. With larger application like the Uber app, this may mean the difference in 30 seconds of an installation time. The last helpful build tool I want to cover solves a problem that I'm sure all of you have experienced at some point, but as you get more developers contributing to your code base, master breaks more frequently. People step on each other's toes, merge conflicts happen in between the time when a CI verification job may have signaled it as okay to merge. And with hundreds of mobile contributors, we were in a state last year where at least once a day we were breaking master, and it was just a complete developer outage. Developers would git pull, rebase their change, only to see it start breaking right away. And they aren't immediately sure if it's their feature that's broken or something that they just pulled in. So productivity would plummet. So we introduced a tool called SubmitQ. This isn't a new concept. It's a tool that validates the diff that it'll emerge successfully after verification and landing has been done. It'll automatically group a bunch of these together and try to rebase them and run a series of automated checks. And it'll help keep master green. And this is crucial to keeping developers productive. This technique has been implemented by numerous open source communities. A great example of one that's fully open sourced right now is the Kubernetes project. With our project structure defined, compiling and sailing smoothly, it's time to move on to how we are actually building the app. So in 2016, a focus group of engineers was charged with researching and creating an architecture for a platform of mobile development that will allow us to scale for the next few years. They researched many existing architectures and eventually proposed our own solution, which was codenamed Presidio at the time, that would become the foundation of many of our apps today. There were a number of goals stated with this project. The first is that we wanted to be able to define the difference between core code that's absolutely required for an end user and code that's optional and could be spared to turn off if it was buggy or there was an issue. And with scale only expected to increase in hiring and the number of products that we were delivering, we wanted to set up a foundation that would last for a number of years. We wanted to create guidelines and rails for developers and designers to work on together to allow fast, consistent, and reusable features across multiple apps. And you can't define success without properly measuring it. And it shouldn't be left up to the individual team or developer to figure out how to measure the application-wide metrics. So our foundation should provide measuring and monitoring as a first-class citizen. Users rely on our app as a daily utility critical to their lives. Some people drive for Uber, and it's their entire work income. Some people commute to Uber. And to move as fast as a company, people can't be afraid of breaking the application for these folks that are depending on it. So the foundation needs to provide the basis for experimentation without worry. Lastly, our tools should empower a great app experience, not inhibit it. It should be performant and handle things like graceful degradation on low-end devices out of the box. So based on these architectural goals, we investigated many of the well-established architectures in the space, like MVC, MVVM, and Viper. And we found for each that there were downsides that made them not quite work for us. MVC and MVVM commonly has hard-to-maintain fat view controllers. Our old writer app was built on MVC, and a request class that started as 300 lines of code quickly reached thousands of lines of code and became unmaintainable. The code base became fragile, testing was difficult, and updates slowed down. We liked a lot of things about Viper, but it included much more explicit separation of concerns and easier testability. But if we were to use a pure implementation of Viper, it would couple the application state to the view tree, and it would leak business logic through the presenter. So based on those principles and the inspiration from Viper, we created an open source to cross-platform architecture pattern and framework called RIBS. It's implemented natively on Android and iOS, but the domain language and the concepts are shared between iOS and Android, so developers can work together for better collaboration and design. A RIB unit is defined by a builder, which creates the other components of the RIB, an interactor to manage business logic, and a router to help with routing between these RIBs. And since we wanted the application state to be tied to the business logic as opposed to the view tree logic, RIBS encompasses an optional view and presenter to manage the data model translations and layout animations and that sort of thing. Our writer application represented by business logic state trees where each node here is one RIB unit. Each one of these will only be instantiated, attached, and active when it's needed, based on the user's workflow. Let's walk through this with an active RIB tree while the user's requesting a ride. Initially, only the RIBs related to the home screen will be active, in memory, alive. And as the user moves the car through the car request flow, confirming their ride, the home RIBs are detached and a confirmation RIB is attached. Followed by a refinement choice where the user can refine the location to be picked up. Maybe they're at a venue and need a specific door to be picked up. Finally, all the pre-trip related RIBs are detached, and an on-trip branch is created and attached. Communication between RIBs was designed to satisfy the open-close principle. For communication downwards, we rely heavily on our X. A stream is placed on the DI graph by a parent RIB, and then an emission is made on our stream that the child subscribed to. For communication upwards, the child RIB would define an interface that the parent implements. Then the child would execute against that method. With the backbone of our application defined, I now want to walk you through some of the tooling that we use both to support RIBs as well as to generally empower better mobile development at scale. To assist developers with RIBs by reducing the boilerplate required for them when they're creating them, we also released an IntelliJ plugin that lives in the same repository on GitHub. This will auto-generate all the required classes and boilerplate needed to wire up the components. When we first did this, it's using Dagger under the hood for your builder. It's generating these components, and as you attach the RIBs, you're getting parent components and child components, and you're managing this. But one of the bigger complaints that we got from our hundreds of mobile developers was that, and we've heard it from similar peers at other big companies like Square and Dropbox and Airbnb is that Dagger has a high learning curve, and it's too complex for a large code base with a lot of deeply nested scopes, and granular scopes especially. Tasks like wiring up those dependencies from the parent down to the children, when you can't use subcomponents because they won't scale and it has to build the entire DI graph. The boilerplate of just wiring up the nested components to themselves, or debugging when a dependency-related build failure was missing, are all common complaints we've heard. So we built Motif to solve this. Currently, it's open sourced as a pre-release, and it's being developed in the open. Motif is a code generator that sits on top of Dagger. It's an abstraction on Dagger. And it provides a full interop with the underlying DI graph. So it gives you a lot of flexibility in moving back and forth between Motif and Dagger. And we found that it's a much simpler subset of APIs that in some architectures are much more well-suited to understandability, while maintaining the full flexibility of Dagger if it's needed. So let me walk you through an example of what Motif is doing. Here, I've defined a very basic scope using the Motif scope annotation on an interface that will serve as a container for the objects that can be created by the scope. We can then explicitly declare a scoped interface that will generate the appropriate bindings in Dagger. Then we annotate a factory class with the Motif objects annotation to provide our dependencies. And we explicitly declare which of these is exposed to our children. And that's all you need for writing a basic top-level scope. Now in our child scope, we're able to use the database dependency provided by the parent. This project isn't designed to replace Dagger, but it works well when the architecture is suited to it. And we also released an IDE integration via a plugin to IntelliJ that allows you to explore your DI graph, and it makes debugging it simpler. There are a lot more features to check out in this. And like I said, it's not a replacement for Dagger, but it does simplify some use cases. And when you have these deep nested scopes, a deep tree of them, then it is a pretty good option. One of the most important pieces of functionality that was built into the new writer and driver app architecture was the ability for us to distinguish between core code and optional code backed by a plugin system that we can enable so that developers have safe rails to build on, and that we can turn off functionality that's inhibiting users. We recently open sourced a metadata generation tool called Crumb. It's the backbone of this sort of functionality. Crumb enables you to generate metadata in downstream dependencies that act as providers for information. And then upstream parents can consume those in the annotation processor. And then we combine all that in a tool like Java Poet or Kotlin Poet to generate code based on this metadata. In this diagram, taken from the example in our public repo, you can see how the plugin system is here for collecting dictionary translations. Implementations as plugins are defined as libraries that could be managed across compilation through CodeGen to be collected in the parent app at the end. In Crumb's repo, you can see this full example if you're trying to grok what this is doing. But in our applications, we built a much more complex version of this. And it powers an entire A/B testing framework and plugin system that connects to our backend service to enable feature switching on these things. This allows the rollout of a new feature behind a plugin. So in the event of a crash or an outage, we can disable that entire feature remotely. Here's your typical plugin. It contains an identifier that can be referenced against a copy of enabled experiments, the information to determine if it's applicable for the dependencies you provide, and the ability to create the underlying plugin. We then provide a plugin point class that lists all the plugins that adhere to a specific interface for that common dependency. Finally, we're able to utilize the plugin point to request a specific plugin and act against its API. In this version, I've added A/B testing, a generic A/B testing framework as the parameter required to construct this plugin point. So I've walked you through a bit of the high-level idea that a rib tree can attach and detach branches when needed. Of course, this implies that there are create and destruction life cycles associated with a rib as well. I also mentioned that the rib tree uses RX streams to communicate down to its children. As many of you are probably guessing, this could be vulnerable to a lot of memory leaks if cleanup isn't done properly. To address automatic unsubscription from RX streams, we created a new library. Say hello to Autodispose. Autodispose provides a simple API for you to use in your RX chain to manage automatic binding of an RX stream to a scope for disposal and cancellation. The idea here is simple. You construct your chain, like any other. And then before subscribing, you can simply call the static auto-disposable method with one of 3 overloads for convenience. The maybe semantic, modeled after take until, which takes an observable that emits a signal to signal the completion of the stream. A lifecycle scope provider, which is an interface that exposes lifecycle events you care about to signal completion. This would be used to explicitly tie the subscription to lifecycle events of an object. And a scope provider, which is an abstraction that allows objects to expose, control, and provide their own scopes. They return an auto-dispose converter object that implements all the RxJava converter interfaces for use with the as operator in RxJava types. Also, auto-dispose exposes a lot more functionality to make it more powerful, including Kotlin extensions, Rx lifecycle extensions, adapters to plug into the architecture components, a plugin system modeled after RxJava's plugins, an error-prone checker, and more. Another area that can be really challenging when dealing with dynamic app state is how to reference a static snapshot of a tree. A common area that we've seen that would be problematic around this is with deep links, when you have a string that references a state of the rib tree that needs to be achieved. So to address this, we designed and launched a framework that interops with ribs called workflows. It's a framework that describes asynchronous reactive steps. And the workflow framework is composed of 3 parts. The first is a step, which is a single action to be completed. The second is an actionable item. It's an interface representing the steps a specific rib can accomplish. And the last is the workflow class itself. Each one of these is expected to describe a series of steps required to achieve its goal. Here's an example diagram of a workflow handling a single sign-on deep link. Once the plugin point creates a specific workflow to handle the deep link based on its isApplicable method, the workflow framework will describe the number of steps needed to progress through each one of the rib tree states. Using a series of implemented steps on each actionable item, which is an interface to describe a specific interactor within a rib node, each interactor knows how to progress to the next state. So we're able to navigate multiple ribs down to do the single sign-on oriented one. Here's the code to handle that meat of that workflow. We have a series of steps defined that will walk from root all the way down to the main interactor before finally attaching a full screen rib that is referenced here as the single sign-on rib. For example, in our root interactor, we define a step that waits until the user signed in and then triggers the next step. So if the user's already signed in, this will trigger immediately. Otherwise, it will wait for the user to sign in, and then it will continue to the flow to the next step automatically. So we've covered ribs and a variety of tools to help make them more usable. Let's move on to tools not as directly related to ribs that we use to scale. As Android apps grow, providing common features and consistency across UI elements becomes challenging. And as we have a number of teams building UI functionality, it's important to keep the app looking consistent for the end user and, more importantly, behaving consistently, especially across apps. To keep consistency for the user, we collaborated with our designers to create a style guide for downstream teams, also known as program teams inside of our company, and they consume this. Now, this solved one part of our problem, but it introduces some more. First, since Android owns the Vue base classes, this often means that we have to maintain a large set of customized base views. When a bug fix or feature is added into one, it must be copied or delegated from the others. We'd like to we'd like to see this resolved with the help of Rx binding APIs and accessibility and analytics. All these things, we're having to do a lot of those sort of implementations, one-off on each one of these base views. Second, as the organization grows, what ensures that downstream engineers use the appropriate base views and they don't just spin up the regular Android one, as opposed to, or create their own custom one, then lose out on that functionality. So to address the first point, we built and released a tool called Artist. Artist is a Kotlin-based code generating tool that will allow you to generate a base set of Android views. Artist-generated views are created using a stencil and trait system. Each view type is declared with a single stencil, which is comprised of a set of traits. All of this comes together to create an easily maintainable system of stencils and traits. A stencil describes the view to be generated and has properties that can be configured, whereas a trait has a hook into the stencil's code gen where you can implement specific pieces of functionality that are shared across multiple stencils. Think of it like a mix-in. Here's a basic example of a trait. Here we want to create a convenience method for checking the visibility states of a view. We'll iterate through the visible states, and then create the convenience methods is visible, is invisible, and is gone. And for each of these, we'll use a tool like Java Poet to write the meat of the method out. We'll then write up our stencil, specifying the view information to be generated, as well as listing the traits that we want to be added to that view that we're going to generate. Now we can see what a generated view would look like. For more info about Artist, as well as detailed instructions on wiring it up to your Gradle script, check out the public repo and the README. And recently, just last week, we open sourced a tool that works pretty well with Artist called Stylist. It's a new tool that works great together, and it generates Android themes. So whereas Artist is generating your base views, Stylist is generating your base themes. It uses a similar model of stencils and what we call style items, which is a grouping of items inside of a theme. We're able to define and generate multiple sets of themes with common functionality from different parents. For example, if you want to extend both from the light and dark theme in AppCompat, and you want to have all of your customizations, this would allow you to generate that in one maintainable location. And Stylist will then create identical sets of themes from both parents, providing much greater maintainability as you develop and evolve your app. In addition to the tools to generate the proper views and themes, we make extensive use of linting and reporting rules to give developers immediate feedback or on inappropriate use or potential errors in their code. Here we have a simple lint that extends the resource XML detector. When this discovers usage of the standard switch compat as opposed to our own generated U switch compat from Artist, it will throw an error to the developer informing them to use foo switch in this example. Secondly, we automatically add blocking reviewers to our code review process if certain behaviors are used or adjusted using Herald, which is a part of the Fabricator tool suite. It's an open source code review tool that we use that was built by Facebook. Herald is a powerful part of our tool chain, and as teams grow, it gives us an automated way to being alerted when people make changes that may be critical to us, and other folks can set that up for alerts that they may view as critical to them. In addition to the errors I mentioned, there are also a slew of others that will impact software projects. The larger the project grows, the more likely it is to be affected by common and avoidable errors. And one tool that we use on our mobile projects is ErrorProne. It's a fast compiler plugin built by Google that will fail at build time with common errors, and it has an easy-to-write checker plugin system. For example, in this piece of code, we're injecting our object graph after we've called super.onCreate. This can cause configuration change bugs and issues with reattached fragments that the system handles. So ErrorProne would halt the execution at build time and give you a compile error to let you know about the error so that you could resolve it. And ErrorProne makes it easy to write the new checkers for error types. When we looked at the benefits of Kotlin and Swift, one of the obvious wins around that was how it handles nullability as a first class, how it throws it in your face at compile time. And so using ErrorProne as the base, we wrote and open sourced a tool called NullAway. And this helps solve that billion-dollar mistake at compile time. It's fast, it can run on every build of your app, and it has little overhead to use. With a quick example, we have a method that takes X and then it prints it out. And in this case, we're sending null. By default, NullAway assumes all unannotated parameters are non-null. So at compile time, NullAway would alert us to this issue and stop. And we can fix the issue by adding an annotation. However, NullAway would still fail again on the printing usage unless we added a null check as well, similar to Kotlin, prior to us using X. At Uber, we combine ErrorProne with another validation tool that we've created called Rave, Runtime Annotation Validation Engine. Rave uses the annotations already present in your data model to generate validators on dynamic data to ensure that it adheres to the contract that you expect at runtime. First, we would want to create a validator factory. Here, the sample factory generated validator is generated once a model references the sample factory class using the @validated annotation. Let's assume we have a model that's being hydrated from JSON on a network request to indicate it was a match was made or not. We're defining a Rave factory class to generate the validator with. We then reference the factory we created, and we're being specific that the match variable is non-null, and that it must be one of the two statuses that we defined here. Now, when we indicate to Rave to validate this model, it'll use the validator to throw an exception if something is wrong. Now, this would be easy to put into a retrofit adapter to efficiently validate models on deserialization. While Rave is powerful, and we use it when we have dynamic data, I would highly recommend taking a different approach altogether. And for your networking models and your API requests when it's possible. And that's using a tool like protobuf or Thrift to have the same generated model that lives both on the client and on the server, to guarantee the states and have more efficient network traffic using a binary protocol. These tools typically allow you to define language-agnostic spec and then generate class files for various code bases. For most of our main models and services now, we've done this. We primarily generate everything using a stack built on top of Thrifty, which is Microsoft's mobile-focused Thrift compiler. This Thrifty takes a similar approach to Square's Wire for protobuf, and then it generates a much smaller number of classes from the spec for more efficient uses on mobile. Lastly, as I said, this talk isn't a deep dive into these tools today, but it should be a starting point for you to think about opinionated scaling of your app. And here's a list of all the open source projects that we covered today. We're looking for more contributors, and we're looking for feedback. So please get on there and get involved, try them out, tell us what you think, tell us where there's issues, send PRs. And many of my colleagues have done great deep dives into some of these topics. I'd recommend that you follow up by watching some of these later if you're interested in understanding some of the architecture-specific stuff that we've done. And of course, stay tuned for more open source projects coming later in the year. We're working on a bunch of great stuff. Thanks for attending today. I hope these provide some pointers for you to think about scaling. If this sort of work interests you, we're hiring both in New York and in San Francisco. I'll be around to take questions after the talk here, and then we have a booth out there, and feel free to come grab us and talk. We're here to talk about these cool projects. Thanks.